Okay, in this problem, we're asked to calculate the acceleration of a slide wire as it's specified. We have a couple choices in order to figure out how to solve this problem. The main quantity that we're looking for is the current that is induced in this circuit as a result of the bar moving. We could use Faraday's law, but since we're dealing with a moving conductor, it's also possible to use the concept of motional EMF, which I write down an expression for right here. So if we integrate all the way around the loop, we can figure out the EMF induced just by computing this integral. Well, if we look at the wires that are involved in the problem, the only thing that's moving is the bar. Therefore, this integral is just going to be along the bar. If we calculate this quantity, we can calculate the EMF induced. So we need to define a direction for dl. If I just draw a little sketch of the bar, we can define dl as being up along the bar. In this case, v is pointing to the right, b is pointing into the page. So it turns out that v cross b is actually parallel to dl. If this is true, we can write down an expression for the EMF. V and B are at 90-degree angles, so the cross product, the magnitude of that is just VB. We're integrating along the direction dl. V cross B points in the same direction as dl, so the dot product goes away. We're going from a distance of 0 to L, where the L is the length of the bar. So given this expression for the EMF, we can calculate that the induced EMF is equal to V times B times L. Well, once we know this induced EMF, we can actually figure out how much current is flowing. The current that's flowing in the circuit is equal to EMF over the resistance. In this case, that's VBL over R. Now, this gives us the current that's flowing, but what we really need is the force, the deceleration of the bar. So we take this current, we combine it with the expression of the force on a current carrying conductor in a magnetic field, and that's IL cross B. Well, again, we can define L in the direction of the current that points up. B points into the board. And that means that L cross B is going to point to the left. So the velocity is moving to right. The force is moving to the left. That means it does indeed slow down. Let's compute the magnitude of this force. It's equal to the current times the length times the B field. Since you can look up here, you can see L points up, B points into the page. It's a 90-degree angle between the two. So the magnitude of the cross product of L cross B is equal to LB. We have an expression for I, which is given above, VBL over R times L times B. Well, that's just equal to V times B squared times L squared over R. And that's the force that's applied. Now this problem asks for the acceleration, which is equal to ma. So it implies the acceleration is actually equal to V B squared L squared over Rm. All right, so the last thing to do is just put in the quantities and solve for the acceleration. We're given that the velocity is 10 meters per second. The B field is equal to 2.15 newtons seconds per coulometer. That's a Tesla squared. Times the length squared, 0.30 meters. Let's work in SI units squared. Over the resistance. Well, in this case, the resistance is given 0.375 ohms. An ohm is a volt per amp. And finally, we have the mass of 0.45 kilograms. So we can multiply all these things together and cancel out the various units. What we find when we do this is we find the acceleration is 24.7 meters per second.